Hey, folks. We're looking at what I think is going to be a fairly short day today. We're going to look at some examples of isomorphism proofs and how do we go about demonstrating these things. We saw the definition last time. Two graphs are isomorphic if, when we create a bijection on the set of vertices, or at least it's possible to set up a bijection on a set of vertices, there is a bijection, then we automatically get a bijection on the set of edges as well. So informally, it just means that the only structural difference between the graphs is the names of the vertices. If I can rename the vertices of one graph to the other graph and then have them be the same, then they are isomorphic. So as an example, we did this example last time. These two graphs are isomorphic. That if I start with the vertices and I send A to E, then B to F, then C to G, and then D to H. So I am renaming the vertices. So this becomes E, F, G, and H. Then this graph and this graph are exactly the same in terms of their connections. EF is an edge, EF is an edge, EG, EG, EH, EH, and so on and so forth. So that's the idea, that when I look at the edges, AB becomes EF, and that's an edge. And then AC becomes EG, and that's an edge. And AD becomes EH, and that's an edge, and so on and so forth. All right. So let's try this example here. We would like to prove that these graphs are isomorphic, which means we have to find a bijection that works. And one of the things that we might start with to try to help narrow things down is to label the degrees. Okay? This might help us to eliminate some possibilities. So this vertex A has a degree of 3, but vertex B has a degree of 4. 3, 1, 2, 3, 4. 1, 2, 3, 4. F is 1, 2, 3, 4. So if I go over here and count, 1 has a degree of 4. 4. 1, 2, 3. 4. 4. And 3. Aha. Okay. So first thing I notice is that I have two vertices of degree 3. And so my renaming, when I start to prove this, my vertices A and C are going to have to go to 1 to 3 and 6 somehow. So let's try setting A to 3 and C to 6. See if that's going to create a problem here. Okay. Then I notice that 5 is connected to both 3 and 6. And so is 1. 5 and 1 is connected by this arc over here, and then straight down to 6. So 5 and 1 are both adjacent to 3 and 6. And so those are going to have to be my B and D, because B is adjacent to both A and C, and D is adjacent to both A and C. So we might send B to 1 and then D to 5. I'm not sure that it's this order. It could be the other order, but let's start with that and see what happens. And then finally, E and F then have to go in the last positions, but I notice that E connects to C and D, which will eventually be 5 and 6. 2 connects to 5, but not directly to 6. But 4 connects to 5 and 6. And so I think E needs to go to 4, and F needs to go to 2. And let's see if that works. If we do this, then every edge in this graph should map automatically using these rules. So I'm going to switch colors, and we're going to go through all of these edges. The first edge is AB, which goes to 3 and 1. So this is AB. And it goes to this edge here that goes from 3 to 1. All right, I have an edge down here from A to D. A to D will go from 3 to 5. And that will be this edge here that goes from 3 to 5. All right. My third edge is going to go from A to F. A goes to 3, F goes to 2. So 3 to 2 is going to be this edge here. So far, so good. Haven't missed anything yet. All right. 4 is going to be an edge from B to C. And under these rules, B and C go from 1 to 6. Well, right there is 4 to 6. All right, or 1 to 6, sorry. Oh, all right. So then we have BE. B goes to 1 and E goes to 4. So I need now an edge from 1 to 4, and that would be this one. This will be 5. All right. I have an edge from B to F. So this will be my 6th edge, B to F. B goes to 1 and F goes to 2. Okay. So let's see if we can find 1 to 2. That's actually right there. That's easy. That's edge number 6. All right. We don't have too many edges left. C to D. This will be my 7th edge. C goes to 6, D goes to 5. And right here is the 7th edge from 6 to 5. C to E is right here. This is edge number 8. C to E is 6 and 4. And that's right here. All right, and now what's left? We have DE and DF. And EF. I'll go ahead and write these down. So this is 9, 10, and 11. All right, DE goes to 5, 4, which is this edge here. DF goes to 5, 2. 5, 2 is this one here. That's 10. 11, I don't know. Let's see. 11 is from E to F. E goes to 4. F goes to 2. That's going to be this edge right there. Okay, that took us a while to work through all the edges, but I picked a mapping of the vertices. And when I picked the mapping for the vertices and applied that mapping to the edges worked with the mapping as well. That's the idea, that an isomorphism is one in which there's a bijection of vertices and a bijection of the edges, and they're compatible with each other. So it's not just having the same number of vertices and the same number of edges. We have to check for that compatibility requirement as well. Okay? So this is a proof, though, that graphs are isomorphic. Because it's the definition just says we have to show that there is a bijection. We don't have to show for all bijections. We don't have to show this for everything. And so if you can just actually show me that there is a bijection and this is it, then this bijection works for the edges as well. And so we get compatible bijections for vertices and edges, and that's what we need for isomorphism. All right, let's try another example. Let's try proving these graphs are not isomorphic. So we need to figure out some reason why we're not going to be able to create an isomorphism here. So let's start with, again, checking degrees and see what we get. A has the degree of 2. F has a degree of 1, 2, 3, 4. B has a degree of 4. 2, 4, and 2. All right, so over here, every vertex has an even degree. If we do the same thing over here, this has a degree of 2. This has a degree of 3. 1, 2, 3, 4, 4. 1, 2, 3, 4. 4, 1, 2, 3. This is only 3 again, and then this is 2. And now we have a problem because the degrees are not going to match up. And so as a proof of isomorphic, I have 3 vertices here of degree 2, but only 2 vertices here of degree 2, which means one of these vertices is going to have to map to something that has a degree of more than 2, and then that means there's got to be an edge over here that gets left off. Okay? So prove these graphs are not isomorphic. They have different degree sequences. So that's the proof. Okay. All right. So sometimes it can be hard to tell just by looking whether 2 graphs are isomorphic. This looks like it's going to work out. Every vertex, this has 8 vertices, this has 8 vertices. All of these vertices have a degree of 3. All of these vertices have a degree of 3. And so on the surface, it looks like we don't have anything that's going to work. And so what can happen is we can try to see what happens and see whether we succeed or fail. Okay? So what I'm going to do first is I'm going to argue that the graph on the left is symmetric, where every vertex is either a corner of a square and then a diagonal that connects one square to the other. And this graph is symmetric, where every vertex is part of an octagon and the border of 2 triangles. And so it's not going to matter where I send A to. So let's go ahead and start by sending A to 1. So we'll start by sending A to 1. All right. And now one of the things I notice is that A is connected to B, E, and D. So A is adjacent to B, E, and D. And 1 is adjacent to 2, 5, and 8. All right. So B, C, and D have to match in some order to 2, 5. I'm sorry, B, E, and D have to match up to 2, 5, and 8. But looking ahead even further, B and D both connect to the same vertex, C, but E does not connect to C. And so is there a vertex that will help me identify which ones are B and D? So 2 and 5 don't, they both connect to 6. So if B and D were 2 and 5, they would connect to 6, and 6 could be C. 2 and 8 both connect to 1. That doesn't help because we've already left side 8 to 1. 5 and 8 both connect to 1 also, and they don't. That doesn't help either. So B and D are going to have to go to 2 and 5, and then E will go to 8. So E now has to go to 8. All right, so this was our A, and this is our E. I'm just trying to keep everything straight here. All right. So then we know now that B and D go to 2 and 5, but H connects with D and E. So we need a vertex that connects with either 8 and 2 or with 8 and 5. Well, the problem is that A is one of those vertices. We need a second one. 8 connects to 4 and 1 and 7. But 2 connects to 1 and 3 and 6. There is no other place where 1 and 2 connect. And so this can't be 2, and so B has to be 2. Try that. Let's see if that works, okay? Well, then by elimination, D has to go to 5. And we still have this H problem. Because H has to connect to 5 and 8. And 5 connects to 4, 6, and 1. So 5 connects to 4, 6, and 1. But 8 connects to 4 and 7 and 1. So we can send H to 4. All right. So we with okay so far. A is 1, and it connects to B, D, and E. So I'm going to send B and D and E to the 3 vertices that are adjacent to 1. And then we also have an H. H is connected to both D and E. So we need it to be connected to 5 and 8, and it surely is. Okay. Oh, well, if we keep going, then F has to connect to 2 and 8, B and E. So what connects to 2 and 8? Well, 2 connects to 1, 3, and 6. So 2 connects to 1, 3, and 6. 8 connects to 1, 4, and 7. The only thing that they connect to in common is 1. But that's a problem because I've already assigned 1 to A. And so F has no candidate. There's no way to assign F. So we tried to make an isomorphism. We failed. And something about building this vector, this point F, was a problem. And so let's see if we can figure out what happened here. The graph over here has a lot of cycles of length 4. So this was 4 elements in a row, and this is 4 elements in a row, and then the whole thing was 4 elements in a row. And so vertex A is a part of 3 different quadrilaterals. So if I look at the quadrilaterals, I can form from 1, okay? Then I can go from 1 to 2. If I go from 2 to 6, 6 to 5, and then back to 1. That looks twisted, but it's a quadrilateral. It's 4 sides. Okay, that's if we go to 1 to 2. If we go in the other direction, we get 1. Let's see, 8, 4, and 5. Building this sort of hourglass pattern out of this side also. All right, so quadrilaterals from 1. Including 1 are 1, 2, 5, 6, and then 1, 3. No. 1, 2, 5, 6, 1, 4, 5, and 8. All right. So now we need a third one. So we have 1, 2, 5, 6. That's a big one. And then 1, 4, 5, 8. That's this one over here. And then we have 1, 8, and then this other edge that's going to be a little tricky to figure out. Well, it has to connect 1 with the vertex that E represents. And so it has to include 1 and 8. And it has to include 2. So it has to include these 2 sides here. I'll change colors again. So what we're looking at is these 2 sides being sides of a quadrilateral. So then we need the opposite vertex. And so we need a vertex that connects to both 2 and 8. Well, 3 connects to 2. Where'd my pen go? It's over there, sorry. There you go. All right, 3 goes to 2, but it doesn't go to 8. 4 goes to 8, but it doesn't go to 2. 5 doesn't go to 3 or 8. 6 doesn't go to 3 or 8. 7 doesn't go into 3, but it does go to 8. But that's still not going to be any help. And so I can build from a vertex like vertex A, I can build 2 quadrilaterals, but I can't build a third one. If I try to build a third one, there's no place to put that opposite corner. And so these graphs are not isomorphic. Isomorphic. Okay. So that's probably one of the harder kinds of isomorphism problems. You just dig in and try to build it and then find out where the contradiction lies. Okay? So that's the same problem we just did. Yeah, example, decide with proof whether these graphs are isomorphic. So we've done that. So a couple things to check. Check the degrees. That's an easy thing to check. If they don't have the same degrees, they cannot be isomorphic. If they do have the same degrees, like in this example, then you just have to sit there and start plugging away at possibilities and showing that something isn't going to work out, or does work out, in which case you're done. And if it does work out, it's easy. You just show me the list of vertices and show me the list of edges. All right? Y'all have a fantastic weekend. Take care of yourselves.